neighborhood interested citizen.
I'm Alma Costellas. I'm visiting. I work as an environmental planner in the San Francisco Bay Area.
Welcome.
I'm Joe, the community development manager undergrad.
I'm Ed Anderson. I'm a traffic engineer at ITS unit UDOT.
Beyond within public administration.
Chris Monsier, civil and environmental engineering faculty.
Great.
Dave Hampston, graduated from here 2003 and are currently an unemployed transportation planner.
Scott Cohen, I work for UDOT.
Great.
I'm Evan student. I'm an undergrad here.
I'm John Libby. I'm a faculty member here.
I'm Emily Moore. I'm an NPH student here. Erin Anderson, community development undergrad.
Robert Esposito, civil engineering undergrad.
Bob Crane, also civil engineering undergrad.
I'm Darren Munn, Master's in Public Policy here at Portland State.
I'm Matthew George. I'm a civil engineering undergrad.
I'm Ian Chester. I'm a student in statistics and social science, focusing on political science and urban development.
Very good. And I'm Rob Bertini. I'm a faculty member in urban studies and planning and civil environmental engineering. And I think we will get started with the live broadcasting part of the presentation. All right. So welcome to the Friday Transportation Seminar here at Portland State University. And one of the best parts of this job is to actually see our students graduate and see them present their work for us and for them. So very happy to introduce Michael Wolfe, who is finishing up his Master of Science in Civil and Environmental Engineering. And he's presenting his thesis topic, which is the effects of aggregation on arterial performance measurement. And maybe, Michael, if you want to say a little bit about how you got here to this program. Sometimes people are interested in hearing because
Sure.
You didn't start off like some of these guys as a civil engineering undergrad.
Yeah.
I'll
well,
turn it over to you, Michael.
Sure. Yeah. Well, my name is Michael Wolfe, and I graduated in 1996 from Macalester College in St. Paul, Minnesota, with a degree in mathematics. And I spent 9-10 years working as a computer programmer before I figured out what I really wanted to do. And it turned out that it was sort of the nexus of my love of bicycling with my love of mathematics and thinking about things in a sort of an analytical way, and that led me to transportation engineering. And so when I figured that out, I squirreled away some money and saved up and then came back to school. So that led me to where I am today. So good afternoon to all of you. Thanks for coming out. I'm going to talk to you, as Dr. Bertini said, about my thesis topic, which was the effects of data aggregation on measuring arterial performance. So here's an outline of the talk that I'll be giving today. I'll start off with some of the background of the problem of measuring arterial performance. I'll go over some of the concepts that provide the foundation for the analysis that I did. Then I'll talk about the simulation that I created to test my ideas, and then about the analysis that I did on the data that I got from the simulation, and finally wrap up with some concluding remarks. So I had 3 objectives in my research. The first was to examine methods of generating arterial performance measures from point observer data. And when I talk about point observer data, what I'm talking about specifically in this case is loop detector data. Loop detectors are ubiquitously installed. They're in just about every city around. They're well understood. And they provide their data frequently to centralized locations such as an operations center. So they would be ideal for leveraging for use in providing arterial performance information if we can figure out just how to do it. The second objective was to understand the effects of data aggregation on derived performance measures. As ubiquitously as they are installed, sometimes there are questions about their density, and oftentimes loop detectors provide their data in chunks, either in chunks that are on a sort of a signal cycle by signal cycle basis, or maybe in 5-minute chunks or even 15-minute chunks. And I wanted to understand just what effect that had on the quality of the information that we could get from these data sets. Having done both of those things, then the third objective was to propose a method for estimating arterial performance based on signal system data, based on the levels at which we can get it now, and based on and to provide recommendations for maybe updating, or rather improving the quality of the data that we can get from them so that we can reach this goal of providing arterial performance based on loop detector data. So here's some of the work that's been done on the problem of arterial performance. This first study is typical in that it decomposes travel time into two components. Your free flow travel time, which is the amount of time that it takes a vehicle to traverse a given roadway segment unimpeded. So, and then the second component is delay components, which consist of interactions with other vehicles, interactions with signals, acceleration and deceleration, that sort of thing. And the second study took a sort of a novel approach. It created these virtual probes and applied an iterative algorithm to them to, based on the relationship of each of these virtual probes locations to each other and to intersections and to signals, to derive vehicle behavior from limited data sets. The third study was concerned with just how useful stop bar detector data was in terms of being able to provide arterial performance information. When you have a detector located at a stop bar, then there's some concern about the effects of the interference of nearby traffic signals, which will mean that you're going to be detecting a stationary vehicle a lot of the time. Fortunately, he answered in the affirmative that there was still useful information to be gleaned from these stop bar detectors. Then this fourth entry was concerned with using loop detectors to evaluate signal performance, which is a big part of arterial performance. And then finally, this last study, a collaboration between the Texas Transportation Institute and Kittleson, revamped highway capacity manual urban street performance evaluation methodology using a variety of methods, including traffic flow theory and application of probes of various types, including investigating the use of transit vehicles as probes. So what we have here is a time-space diagram, and I'll be showing you a lot of these. In this case, it's a time-space diagram depicting freeway performance as measured by a set of stationary inductive loop detectors on the freeway. And it's called a time-space diagram because it has time on the x-axis and space or position along the freeway on the y-axis. And each of these lines that runs vertically represents the movement of one vehicle down this segment of freeway over the section of time. And because you have position or location on the y-axis and time on the x-axis, it leads to the very convenient conclusion that the slope at a given point of one of these trajectories is proportional to the speed of the vehicle at that point in time or space. You can ignore the background colors. That is known as a contour plot, and it represents the density that was detected at those locations, but it's not something that I consider in this talk. And so you can see that inductive loop detectors do a pretty good job of giving you a picture of what's going on a freeway. This picture represents some research that I did and was involved in that tried to take the methods that we use for generating freeway performance information and applying them just straight across onto arterials. And this attempt was made on data that was aggregated over 5-minute chunks. And you can see that we might not be sure about how accurately this actually represents what's going on. You get some steeper trajectories when there's more congestion, more density, but clearly, these 5-minute chunks are rather large, and they represent more than 2 average signal cycle lengths in this corridor. And you get some trajectories that are crossing each other, which is sort of counterintuitive when you think about it. You wouldn't expect that vehicles that entered a roadway segment behind you would end up leaving before you. So we have some reason to be skeptical about this. And so this motivates my research. The work on this project motivated my research to say, well, okay, so is this actually good enough? And if not, what would be better? And how much better data would we need to get in order to give us a really clear picture of what's going on? And so finally, as to finish up the preamble, I want to take a step back and talk about what arterial performance actually means. There are a variety of ways to measure arterial performance, and this just represents a brainstorm that I had of some of those ways. And they're organized by the type of underlying data that you would need in order to calculate each arterial performance measure. So if you had speed data, then you would be able to calculate the things in the first column. If you have count data or volume data, you could calculate the measures in the second column. The measures in the last column would require some other kind of data in order to calculate them. Finally, they're also organized by just what level of granularity of data you would need in order to calculate them. If there's an E next to the measure, then it requires event-based data. You would need to know the arrival time of vehicles at individual detectors. So you would need to have information on a vehicle-by-vehicle basis. If there's an A next to a measure, then I figured that it would be possible to calculate that measure based on aggregated data. So this sort of gave me a sort of a baseline for what I could hope to achieve given various levels of aggregation or event-based data. And these performance measures represent sort of obvious things like speed and travel time, various kinds of speeds, maximum speeds, average speeds, and so on. But then there's some more sort of esoteric measures such as platoon ratio, which the Highway Capacity Manual uses to assess signal coordination to see how effective it is, and things like signal failure, which is the phenomenon when a green phase fails to exhaust a queue of accumulated vehicles. Okay, so enough background. Now on to the underlying concepts. Once again, we see a time-space diagram. This is just sort of a hypothetical time-space diagram with each of these gray lines representing the movement of one vehicle over this hypothetical roadway segment. And you can see I've put a signalized intersection in the middle of my time-space diagram. And you can see the vehicles slowing down as they approach a red light and then speeding up as the light turns green. So there are a couple of different ways that we can measure this hypothetical roadway segment. Let's take a step back and assume that we can build a big tower or send a helicopter up. And we go up there with a camera and we put the entrance of the roadway segment that we'd like to consider at the bottom of the frame. And we put the exit of the roadway segment that we'd like to consider at the top of the frame. And so we just sit up there and we videotape vehicles going by. Well, this would be spatial observation, and from this we can get vehicle density. So if you just take a freeze frame of that videotape at any point and count the number of vehicles that you see on the roadway segment that you're videotaping, you've got the vehicle density. You can get the space mean speed, which is simply you record the speed that each of those vehicles is presently traveling at your freeze frame, and then you take the mean of that. That gives you the mean of the mean speed of vehicles that are in that space at that time. You can get the actual travel time simply just by timing the time it takes from a vehicle entering the roadway segment that you're videotaping to the time that it leaves. And finally, from that, you can get actual delay, which is, once again, it's the amount of time over free flow time that it takes a vehicle to travel a roadway segment. But we don't really have the money to go out and send people up in helicopters or build big towers to view every segment that we might want to evaluate. So frequently we are limited to point observations. And this would be analogous to standing on the side of the street with a video camera and videotaping as cars go by and just looking at a single point. Inductive loop detectors make this kind of observation because they're located at a single stationary point, and they just know what's going on the point in the roadway above them. From this kind of observation, you can get you can get flow data. You can get perfectly good count of vehicles that pass over that point of space. You can get time mean speed, which is simply the mean speed of the vehicles that travel over this point, this location. So if you can take the speed of each vehicle detected at that location and then take the average of those, then you get a time mean speed. However, this will overrepresent faster vehicles on the roadway because you'll have more fast vehicles traveling over a particular point. Based on these speed readings that you take at this single point, you can extrapolate a travel time over a given roadway segment based on just what you assume, the length of the segment that you assume that this detector is telling you about. But as you can see, the extrapolated travel time, which is this blue line on the right, might differ very, very much from the actual travel time. So if that blue line on the right represents the extrapolated travel time of the black line, the vehicle that's detected on the black line, you can see that there's a discrepancy between the extrapolated travel time and the actual travel time. But from this extrapolated travel time, you can also calculate a delay. But and it will have similar deficiencies based on just how good an extrapolated travel time you're able to make. I just point this out to keep you in mind of the limitations of point observation data, because that's what I'll be using in my analysis. Okay, so we've talked about the time-space diagram. I lean pretty heavily on that in my analysis. But another diagram that I look at, I refer to as a cumulative or input-output plot. In order to generate a input-output plot, we need a segment of roadway that is bounded by 2 detectors. And so we add a second detector to our hypothetical road segment. Then we look at the vehicles that are detected at the input location, and we take note of the time that each vehicle is detected. And then we create this second type of plot, this cumulative plot. So once again, we have time on the x-axis, but then we have a count on the y-axis. And so in order to generate the cumulative plot, we just take note of the time that each vehicle is detected, and every time we detect a vehicle, we increment our curve by 1. And so this just gives you a running count of the vehicles that have entered the roadway segment. We can also do the same thing at the outflow location. So we take note of the detector at the outflow location, and we make a cumulative plot for the vehicles that leave our roadway segment. Now, the neat thing is we can overlay the two. And this gives us a picture of the time that it took all of the vehicles to travel the length of the roadway segment. So if you want to know the time that it took any of these vehicles to travel the length of the roadway segment, assuming that they don't pass each other, you can just look at the vehicle number. So if you look here, this is the third vehicle. Then the horizontal distance between those 2 curves just represents the travel time of the third vehicle. And if you want to know how many vehicles are on the roadway segment at a given time, you just take the vertical distance at that point in time, and that'll tell you how many vehicles are between the 2 detectors. So this is kind of a neat, intuitive way to consider this segment of roadway. Another way to consider the segment of roadway, though, is to subtract out the free flow travel time between the detectors, and this gives you a picture of the delay. So the delay for the 4th vehicle is simply this. It's the actual travel time minus the free flow travel time. And if you want to know the delay for all of the vehicles, it's just the area between the 2 curves. And if you want to know the average delay, it's just the total delay divided by the number of vehicles. And so I use this in my analysis. I use this delay plot as my first sort of filter for the travel time estimation methods that I propose. And I use delay because it's sort of more intuitive to look at this picture and tell the difference between some delay and no delay. It's more intuitive to look at that than to tell the difference between a little travel time and a lot of travel time. It sort of suggests its own comparison there. Okay, and then the final concept that I'm going to talk about here is how we deal with aggregated data. In the case of aggregated data, we have to make some assumptions, and I'm just going to lay those on the table here so that you know how I'm approaching them. So for aggregated data, we're going to assume, in this hypothetical case, a single detector, but for this chunk of time, it's broken into 2 aggregation periods. And 2 vehicles cross the detector in the first time period with an average speed of x, and 5 vehicles cross the detector in the second time period with an average speed of y. Well, the first assumption that we have to make in the case of aggregated data is we have to assume that the vehicles are evenly spaced. In the absence of any better information, we just have to assume that they are spaced evenly. That's the assumption that I'm making, and I don't think that in the absence of any. I think that in the absence of any further information, that's the best assumption that we can make. Furthermore, we have to assume that the average speed that's recorded for each of those aggregation periods is the speed that each of those vehicles is traveling, because in the absence of any better information, that's just the best assumption that we can make. And then we extrapolate that average speed for each of the vehicles. And so we get this time-space diagram with these extrapolated trajectories that are based on our assumptions. But we have to keep in mind that once again, this could be very different from the actual picture. The light blue lines indicating some actual trajectories that might create aggregated data like we've shown, but they look very different from what the aggregated data, what the assumptions lead us to. A second issue with aggregated data beyond just these assumptions that we make is that in real time, if we're trying to conduct a real-time analysis, we have to be cognizant of the fact that data is not available until the end of each aggregation period. And so if we detect, we can generate a cumulative plot, but we can't generate anything for that first aggregation period until it's completely over. And so in real time, this is just the best cumulative plot that we can generate, and it really sort of lags behind what's actually going on. However, if we're conducting an analysis at the end of the day or on archived data, then we can get a slightly better picture of what's going on. But the important thing to note is that we can still create a cumulative plot even based on aggregated data. However, once again, we should keep in mind that the real picture might look rather different. OK, so on to the simulation. In order to test my ideas, I created a simulation in vsim 5.0. Very cool. I created my simulation based on data that I got from a SCATS signal coordination system evaluation that went on in a corridor in Gresham, Oregon. This signal coordination system was installed on East Burnside Road in Gresham, Oregon, from Eastman Parkway to the junction with Highway 26. Data was collected from April 17th, 2007 to April 24th, 2007. And the set of data included data from loop detectors. It included signal timing information. And it included probe data. Probe data such as, I'll take questions at the end.
I'm sorry, I don't know what a loop detector is.
OK. A loop detector is a metal loop that is installed underneath the tarmac in the road, and there is an electrical current that is run through this loop, and electromagnetic induction is such that when there's a metallic object over that, it disrupts the current in the loop, and so there's a computer hooked up to that. And so it can tell when there's a presence, there's a metal object present above the loop detector. And so you can get a time of arrival and a time of departure, and you can count the number of signals that are created. You're welcome. Right, so we got data from loop detectors, signal timing information from signals, and probe vehicle data, including average speed, maximum speed, and travel time. I focused in my simulation, for simplicity's sake, just on the three westernmost intersections. This is a satellite picture taken courtesy of Google of the section of roadway that I was considering. There are three intersections in the simulated road segment, just as there are three in real life. All three are signalized. All three have protected left-hand turns. And there are other access points along this section of roadway in real life, but for simplicity's sake, I just assumed that all movements on and off the Burnside Road corridor took place at the intersections. So to create the simulation, my input volumes were taken from loop detector data, and I had a loop detector for each incoming roadway segment on Burnside and on all three of the cross streets. I got the signal timings from the SCATS controller software, and then to calibrate the simulation, I used running times that compared with the running times that the probe vehicles experienced. So here's a picture of my simulation. I just constructed enough of the cross streets so that it would so that I wouldn't have queues running off the back end. And then each of these little blue dashes represents a data collection point. And data collection points I can use exactly as loop detectors. They'll collect all of the information that I might be able to get from some optimized loop detector, such as count, occupancy, and even speed readings. In addition to that, though, it provides me with vehicle IDs, which I can use to construct more or less perfect ground truth trajectories. So I know exactly where each vehicle is on the roadway at all times, within the bounds, of course, of my detector density. So that gives me something to compare my estimation and prediction methods to. So in calibrating the corridor, I created the simulation that I created simulated one peak hour because I figured this was when the most interesting traffic phenomena would take place. The posted speed limit was 35 miles an hour, and my simulation max speeds were slightly above that. And then my simulated average speeds compared reasonably with the probe average speeds. Here are comparison of the actual volumes entering each of the roadway segments and actual volumes versus the simulated volumes. And they're pretty comparable across the board, except for this Kelly-Fairview one. In that case, it turned out that in real life, the detectors, there was a detector in each of 2 lanes, but in that case, one of the detectors was inoperative. So if you about double that, you again come up with a count number that is in the right ballpark. And then on the right, you have my signal timings. Okay, so then to further calibrate the model, I compared my actual probe trajectories with my ground truth time-space diagram and saw behavior that was very consistent. I just simply observed the visualization to make sure that operations were sort of proceeding in a realistic manner, that I didn't have any persistent cues, that I didn't have any cues that were backing up all the way to the previous light. And then I applied this Wilcoxon rank sum test to compare the distributions. Right, okay. So this is the full peak hour of simulated trajectories. It's kind of a mess to look at, but I just wanted to show you the whole thing so that you would know I wasn't hiding anything from you. But when I'm looking at a time-space diagram, I generally look at just a detail of 2 signal cycles. And this is what that looks like. It's a lot more decipherable. But the whole thing is there, no sleight of hand. Furthermore, this is what the ground truth input-output diagram looks like. So the black curve represents the input, the vehicles that go that cross Kelly, and the blue curve represents the vehicles that cross Fairview. And so let me just back up for a moment and say you can see a diagram on the right that Kelly is the easternmost intersection, Fairview is the middle intersection, and Eastman is the westernmost intersection. And so this is just an input-output diagram showing the input, what's going on between Kelly and Fairview in the westbound direction. But again, it's a little bit hard to make out the detail, so usually I'm zoomed in here so that you can see a little bit better what's going on. And so the first filter of analysis will be to compare predicted input and output curves to this actual ground truth, well, simulated ground truth input and output curve, and then to also compare predicted average delay or estimated average delay to the actual average delay. This is just sort of to see the first pass that I took to see what estimation methods might work well. Okay, so now we move on to the analysis. So I looked at I looked at more than 4 different estimation methods. The first one that I looked at was this sort of state-of-the-art midpoint method, which is what we use to very good effect on freeways. And I just wanted to see what the suitability of it being applied to arterials was. And then I came up with several other methods of my own to see if I could maybe take advantage of some of the facts of arterial operations to make a better estimate. So the midpoint method. So here's what the midpoint method is. We start with this hypothetical time-space diagram with 2 detection locations. And we extrapolate the speeds at the detectors halfway to the next detector and halfway back to the previous detector. And then for a given vehicle, we get the most recent speed information from each detector, right? So this just represents the best information that we have at the time. And then to make an estimate as to what the vehicle's travel time is, then we just assume that the vehicle travels halfway to the next detector at the first detected speed and then halfway to the second detector at the second detected speed. And you can see it actually looks pretty good here. It's not too far off. But this is what it looks like when we apply it to our simulated data. It's kind of a rat's nest. And this is what the input-output curve looks like. And you can see that we've got a persistent queue here. The queue never discharges, is never predicted to discharge using the midpoint method. And that's in part because we get these crazy, very horizontal speeds that we're registering right near the green to red phase change. And so the midpoint method is predicting an awful lot more delay than is actually the case. And it's also predicting these persistent queues. And so at least in this case, it doesn't look like the midpoint method is working very well. And I hypothesized that this was for 3 reasons. The first is that we're collecting data at the stop bars, and so we're getting these funny speeds that are highly influenced by the proximity of the signals. And another point is that the midpoint method doesn't take into account this very key piece of information that we have, that we're not going to see any vehicle movement on red phases. And so just because of the nature of the way that we're getting our speeds that we're projecting our vehicles to go at, we could potentially ignore that piece of information that we know sort of as ground, as a baseline. And finally, there's no conservation of vehicles on arterial operations. And so the next 3 methods that I'm going to talk about at least try and take advantage, or take care of the first 2 objections, and they try and minimize that third objection, or at least account for it. So we move on to the vehicle matching method. And so sort of the genesis of this method was I was looking at these 2 hypothetical detectors with detections. And let's just assume this hypothetical case where the entry detector has the detections as shown and the exit detector has the detections as shown. If this is the case, if we had some kind of RFID tag, or if we had some kind of way to identify a vehicle's magnetic signature in such a way that we could label the entering vehicles vehicle 1, vehicle 2, vehicle 3, and we were able to do the same thing at the exiting detector, then we would be able to just connect the dots. And we would know the exact travel time for each vehicle. And this would be perfect. The problem would be completely solved. We would have a perfect answer to just what the overall performance was, between those 2 detectors. We might not be able to account for the places where we're not looking, right? If we wouldn't be able to know what the curve looked like between there. But we would be able to know what time it took detectors to get between the 2 detectors, vehicles to get between the 2 detectors. But we have no way of making that kind of a match in this situation. But looking back at our time-space diagram, we observe that that signals, especially signals that have a reasonable amount of coordination, have a tendency to group vehicles into platoons. And so on this previous slide here, we don't know where the entering cohort matches up with the exiting cohort. In this case, we know that the first vehicle at that green phase at the bottom is kind of going to be the first vehicle at the next green phase in the middle, which is going to be near the first vehicle in the green phase at the top. And so we take advantage of that in the vehicle matching method. We come back to our hypothetical time-space diagram, but this time we throw in the signal phases. So the first step in the vehicle matching method is to, for each entering vehicle, we find its arrival time at the second detector in sort of best case conditions, right? So this is the earliest that the vehicle could realistically arrive. And if it matches to something there, then that's great, but it's usually not going to. So the second step then is to then match that vehicle to the next departing vehicle at the second detector. And we just do this for each vehicle entering the roadway segment. And so from this, you can compute a delay and a travel time just by subtracting the departures from the segment the arrivals from the segment from the departures from the segment. You can see already that this is just an estimate because it's matching several entering vehicles to the same exiting vehicle at the top. But as sort of a baseline, it's not a bad place to start. And here's what it looks like when applied to our actual time-space diagram. And here's what the input-output curve looks like. And I'd say that's a big improvement over the midpoint method. You're seeing little triangles that are definitely underestimating the amount of delay that's going on, but they're in a sort of a proportion, and they're following the tendency pretty well. There are a couple of delay segments sort of in the middle of this curve that are substantially underestimated, but it seems like a good place to start. Well, we have a little bit better information than even the vehicle matching method will give us, and that leads to the saturation matching method. We know vehicles aren't all going to discharge at once, right? We know that they're not all going to take that first match at the beginning of the green phase. And so we start with the vehicle matching method, and we project the free flow arrival time and match to the next departure. But then we save that match. And when we're matching subsequent vehicles, if we match to the same vehicle, or if we match to a vehicle before that, then we just match to the last match plus some saturation headway, right? So this takes into account the fact that we know the realistic spacing between vehicles as they discharge from a queue. And we're just assuming that if we get an unrealistic match, that we will match instead to a saturation density. And so in this way, we can once again predict we can predict delay and travel time. And so this is what that looks like when it's applied to the time-space diagram. And that's actually looking pretty good, if I do say so myself. Just taking into account that, once again, we just know what's going on at each of the detectors, and we don't know exactly what the shape of the curve is going to be between the detectors. And here's what it looks like when it's overlain with the input-output diagram. And so now we're seeing, rather than these vertical all-at-once discharges, we're seeing a discharge at a saturation rate. And so now our output, our predicted output, matches up a lot better with our actual output. The predicted average delay is up to 13.6 seconds versus a ground truth of 20.1. So that's a big improvement over the vehicle matching method as well. Keep in mind that these delay numbers are going to look a lot worse than, say, a predicted travel time, because we're subtracting this scalar of free flow travel time out from them. So once we start comparing travel times, it's going to look a lot better than, off by, 30%. Okay, so there was a fourth method that I'm going to talk about. It's the average departure method. I'm going to talk about that when I'm talking about the travel time analysis that I do later. It's not really as you'll see why. So now I'm going to talk about aggregation. So there are two types of aggregation that I consider. I consider cycle-by-cycle aggregation, where I just know how many vehicles went through in a cycle and what their average speed was during the cycle. But I'm going to make sure that I'm going to operate under the assumption that I also know the signal phasing information for the signals that are adjacent to each detector, because that seems to be very important, especially for some of the assumptions that I'm making with these methods that I'm proposing. And then I'm going to just consider 5-minute aggregated data where I don't know phase information, just to see what that gives me. So first, just to remind you that we can apply the estimation methods when the data is aggregated, just using the assumptions that I went over in the concepts section. So we start with a cycle by cycle. And once again, this is assuming evenly spaced arrivals and evenly spaced departures. And we just apply the saturation matching method to that, just in the way that I described. And this is what that looks like. And there is definitely some imprecision there. And here's what the input-output diagram looks like. But once again, this time we've smoothed out both the estimated input and the estimated output curve, but it still seems to be following the trends pretty well. And it's predicted the estimated average delay isn't quite as good as when we had event-based data, but it's still not too bad. And so it's promising. We might be able to get something out of cycle-by-cycle aggregated data, presuming that we have the phase information. So now we apply the method to 5-minute data. And with 5-minute data, we just know how many vehicles came in during the 5-minute period, and we know their average speed, but we don't have any idea about the phasing. And so this is just the best assumption that we can make. And so even when we have a vehicle matching method or a saturation matching method, these really rely on us knowing what our platoons look like and matching between them. And so this isn't looking too good for us. And the input-output diagram bears that out. Both the estimated input and estimated output curve are this diagonal line from lower left to upper right, and it's not really predicting any kind of delay at all. And so we've lost too much information to make good estimates at this point. So this is sort of a summary comparing those average delays. So what you've seen so far is an average delay number that is applicable to the Kelly to Fairview segment. And so I applied each of these methods not just to Kelly to Fairview, but also to Fairview to Eastman, and then in the eastbound direction from Eastman to Fairview, and then from Fairview to Kelly. And so this just gave me a sort of a broader set of data. And it looks from this that both the vehicle matching and the saturation matching methods aren't bad, but the saturation matching method follows the trends of the actual average delay a little bit better, right? So if you compare the blue and the green bars, they both sort of go down a little bit better in sync than the red and the blue bars, which don't change very much from Kelly to Fairview to Fairview to Eastman. And then this phase matching method was another method that I sort of considered, but you can see it really suffers. It doesn't follow the trend very well at all. When we're dealing with aggregated data, there seems to be a big problem in terms of the delay estimate from Fairview to Eastman. But other than that, both the saturation and vehicle matching method follow the trends from, follow the trends of the actual number. Not too bad. So now I'm going to consider the travel times. And when I talk about travel times, I can bring up the average departure method. Well, this is what we know about average travel time given this hypothetical time-space diagram, right? So if the vehicle detection A1 matches to vehicle detection B1, and vehicle detection A2 matches to vehicle detection B2, then the average travel time is just the travel time B1 minus A1 plus the travel time B2 minus A2 divided by 2. It's just simple average, right? But we can do a little bit of algebra to this equation here, B1 minus A1 plus B2 minus A2 over 2. And if we just do a little bit of commutation, it's just basic, freshman algebra, we can come to the conclusion that our average travel time not only equals that thing in the upper right, but it also equals B2 minus A1 plus B1 minus A2 over 2. And a picture of that is this. So if we know that the detections A1 and A2 are the same two vehicles as B1 and B2, it doesn't matter how we match them. So this is very kind of interesting, right? It doesn't really matter how we match them. And furthermore, if we could do just a little bit more algebra, this is no sleight of hand, I'm not making any other assumptions other than that math applies, we can come to the conclusion that B1 plus B2 over 2 minus A1 plus A2 over 2 is equal to the average travel time. Well, B1 plus B2 over 2 is just the average time of departure of all of our vehicles. And A1 plus A2 over 2 is just the average time of arrival of our vehicles. So we don't even need to match at all. Just assuming that the group of vehicles that arrives is the same as the group of vehicles that departs, then this is just as good as any method that we like to compute average travel time. So now that is a big assumption, though. We're dealing with arterial operations, and so we don't have conservation of vehicles. Vehicles can turn on and off. Another problem is that it's very difficult, it can be very difficult to figure out where your platoon begins and ends. However, given the fact that we have reasonably good signal coordination, it's probably worth a look as to just assuming that the vehicles that go through on one green phase at one light match up fairly well with the vehicles that go through the next green phase at the next light. So worth a look anyway. Right, so here's a picture of just this average departure minus average arrival. Okay, so to conduct my travel time estimation analysis, I first compared the travel time estimates to the actual travel times on a per vehicle basis, and then I also did it on a per signal cycle basis. Per vehicles is a much higher bar to reach, but there are a lot of reasons to consider that the per signal cycle travel time estimation is a little bit more useful, because a vehicle's travel time depends very highly on when it arrives during a signal cycle, whereas it's a lot easier to compare average travel times between cycles because it's not quite as dependent, assuming that you have reasonably good signal coordination again. That wasn't, anyway. Okay, so when I'm comparing travel time on a per vehicle basis, I'm just taking the quantity illustrated on the left, which is actually a delay, and adding back in the free flow travel time, and I'm comparing that to the quantity on the right, and again, adding back free flow travel time. Now, when I'm comparing per cycle travel time, then it's just the area on the left compared to the area on the right. And if we want to talk about average travel time, it's just divide by the number of vehicles that went through the intersection during the signal cycle. Okay, so I compared the estimates to the actual travel times in two different ways. First of all, I looked at the distribution of the ratios for each estimate divided by the actual travel time. And so if my estimates are right on, then they will equal the actual travel time, and this distribution will just look like a big column at 1, right? It'll be a big spike at 1, and there'll be nothing lower or higher. But given that my estimates aren't going to be that good, we're hoping to see a big spike at 1 and then a gradual falling off around as you move further away from 1. And then I also created a linear regression with my, with my estimated travel time as my independent variable and my actual travel time as my dependent variable, just so that I could quantify how well my estimates tracked the actual travel times. So here is an example of distribution of that ratio that I talked about. So this is the average travel times versus the actual travel times for the saturation matching method. And you can see it's not too bad. It's got a big spike at 1, and it just sort of falls off. And so most of the predictions are pretty close to right on. And this is a estimate summary. And so what we're hoping for is we're hoping for variances that are very low and medians that are right around 1. And so the individual vehicle travel time estimates don't look very good. We've got high variances. The medians are right around 1, but the variances are pretty high. Whereas both the vehicle matching method, the saturation matching method, and the average departure matching method are all have pretty good low variances. And so that's for the event-based data. I also applied this to estimates made on cycle aggregated data. And once again, the variances aren't very good for individual estimates, as we would expect. But surprisingly, the estimates for the average travel time over a whole cycle are actually pretty good. And in fact, by at least looking at the variance, they're even better than the estimates made based on event-based data, although the medians aren't quite as good. So then when I created my travel time estimate regression, it was I just created a simple linear regression of the type described by the equation at the bottom there. So it's just a linear, a linear equation. And here's what I got for my coefficients. So what we're wanting is we're wanting A coefficients right around 1, and we're wanting B coefficients as close to 0 as possible. If we have an A coefficient right around 1, then that means that my estimate changes in roughly equal proportion to the actual travel time. And if my B coefficient is around 0, then I'm not introducing any kind of, or I'm introducing minimal systematic error, right? So if my B coefficient is B, then that means, if my B coefficient is 5, then that means I'm consistently underestimating the actual travel time by about 5 seconds. And then finally, I want an R squared that's as close to 1 as possible. that indicates that my regression explains the behavior in the actual travel time very well. And this agrees with the what we saw on the previous slide, that the vehicle matching method, the saturation matching method, and the average departure method function very well with event-based data when you're talking about a cycle average estimate, and not very well for individual vehicles. And once again, it backs up the idea that the estimation methods work very well when they're applied to cycle-by-cycle aggregated data when we have phase information. Okay, so in conclusion, based on the delay diagram analysis and based on the coefficients that I got in the linear regression, I determined that the saturation matching method was the most accurate and the most robust method for making estimates of average travel time over a signal cycle. The signal phase length and offset information is very important, was the second conclusion that I came to the quality of the kinds of arterial performance information that you can get from this data. It's absolutely vital, in fact. And finally, even though the predictions shown, even though they're very comparable, the event-based data did seem to improve the predictions over the aggregated data in that the B coefficient was lower for that regression. Okay, so next steps are to go out and apply this to real data. It's one thing to do it in the lab on a simulation, but it's another thing entirely to see how it works in real life. And ideally, we'd be able to do that with some kind of probe runs to back it up and to see how well the estimates actually came out. One idea that I had after I finished my analysis was to apply the saturation matching method iteratively, rather than, so if I'm applying the saturation matching method to aggregated data, one assumption is that departures are evenly spaced. Well, with the saturation matching method, departures could be evenly spaced, but they could also be spaced at saturation headways. And so rather than making that assumption over and over, then why not start with the departures that I sort of algorithmically created through the saturation matching method and see if that improves its effectiveness when applied to aggregated data. Let's see, the next thing was to examine how prediction methods respond to varying levels of saturation. Yeah, so to see how well they work in non-peak hour conditions, to see if it works very well in undersaturated conditions. And then finally to see how we can use probe vehicles and perhaps transit vehicles to improve the prediction methods. So I'd like to thank Dr. Bertini and Dr. Monsieur for acting as my advisors. They were very helpful and provided me motivation when I needed it. I'd like to thank Alex Bagazi, Rafael Fernandez Moctezuma, and Hal Hagedorn for their technical assistance. I'd like to thank Jim Peters and Steve Boyce from DKS for their help in understanding the SCATS data. I'd like to thank Peter Kuntz from Kittleson for his help with understanding some concepts about traffic signals. And then I'd like to thank my father, Kirk, my sister, Maya, and my fiancée, Allison Slider, for their just moral support.
We need to squeeze in some time for questions. And there are a couple of questions from the web. Maybe you could quickly just let the viewers know where you got the data and what software you use. I think they were asking about the different types of software that you use to produce the results.
So the simulation software I used was vSim 5.0. I performed some data import using Python, a program that I wrote in Python. I performed my statistical analysis using R, which is kind of a steep learning curve, but very cool. I got the data from SCATS, which is a signal coordination adaptive signal coordination software, and then I got the the probe vehicle data from some Excel spreadsheets that it was recorded in.
There's actually one other question about vehicle conservation. Since vehicle conservation does not apply in an arterial network, is there any way devised to account for that in the data analysis? If it could be accounted for, would it yield much better analysis, or does it just not influence the results that much?
Well, yeah, that was something I was very concerned about, and that is a big reason why I didn't expect the individual travel times to sort of regress very well, right? Because when you're comparing one travel time to a corresponding travel time, so vehicle 637 through the intersection, you're comparing those straight across. And so because you don't have vehicle conservation, there's no way to tell whether or not those really do correspond, right, as far as their place in the platoon. And so the chief way that I accounted for vehicle conservation was I said, well, if we can't talk about individual vehicles' travel times, let's see how well our average over the signal cycle holds. Let's see if that is, if we can get a reasonable estimate from that. And that, as you can see from the numbers in the result, it did help. Now, if you were able to account for vehicle conservation, one way to account for vehicle conservation in the real world is to up the detector density. All my analysis that I presented today involved just detectors right at stop bars. But if you were able to put detectors on the far side of intersections and at the backs of queues and in turn lanes, individual turn lanes, and maybe even find some way to detect right turning movements, which are sort of indistinguishable from through movements in the case of these dual use lanes, then you would be able to probably make individual vehicle travel time estimates at least a lot better than I was able to. So.
Another question, then be sure to use your microphone.
You mentioned the upstream queue detectors, how that you might use that for improve some of these with vehicle conservation. Does the corridor not have them, or were they lost, or are they just not recorded in the SCATS data, or were they lost at some point along the chain?
Well, I just used the corridors on the I just used the detectors on the actual corridor to build the simulation. As you can see, I had data collection points as dense as I wanted them to be on the corridor. And I actually did some work looking at the effects of detector density, but I didn't go in. I needed to, I'm already running kind of long, so I needed to cut something out, and I felt that I didn't go into as much depth on that as I did the other stuff. But as far as the real detectors that are out on East Burnside, there's one advanced detector on the interior lane, on the interior through lane. It's 2 through lanes, and there's one on the interior through lane, and then there are stop bar detectors on both through lanes and on the left turn lane. And I was just using, I was just basically using the detectors that were on the through lanes. That answer your question? Yeah. Josh.
I was just wondering, how well did your model match the actual probe vehicle times out there? I saw you compared it to the flow rates and the speeds and everything like that. How well did it match the actual probes out there?
I showed the average speeds there. The travel time distributions, they were better in, I think they were better in the eastbound direction than the westbound direction. Like I said, I used that Wilcoxon rank sum test, and my p-values, I think I had they weren't very good. It was like a 0.21 and a 0.44, but with my sample size was 10 and 12 vehicles, so it was just one more way to look at the data, and I let my faith rest on the fact that the simulation seemed to be operating well, the average speeds matched, and things seemed to be running pretty well. It was kind of the best I could get it. Yes, that's you.
Okay. But you talked about free flow
Mm-hmm.
and the free flow calculation, and how do you go about calculating that number?
how did I get free flow?
So that you can subtract it off of the delay. Yeah.
That's a good question. Well, I mean, part of it is just based on. I think the accepted way to do it is to just look at the 90th percentile speed, right? And so look at it in unsaturated conditions. And I mean, if you were to go out in the real world and try and figure out what your actual free flow speed was for a real corridor, that would be how you'd want to do it, because that would throw out the people who are just driving like maniacs or drunk or something like that. Yeah.
Okay. Can I also ask, were bicycles, would they be included if they were on this corridor?
Oh man. Well, I mean, you do have those little stencils, right, that you can pull up onto with your bicycle and trigger a loop detector, but they'd really totally throw off the data. Yeah. Well, not totally. I mean, because it's one extra detection, right, is what it is. And I'm already not assuming, I mean, I'm already trying to account for a lack of vehicle conservation. So that would just be like another vehicle that disappeared, kind of.
Okay.
Yeah.
Can I ask one more thing?
Sure.
What if it were single lane versus multi-lane? This was how many lanes, this street?
Well, I don't think it would make any. I mean, I don't think that factor alone would make a difference. I mean, if you had a single lane street, you might expect more like turning movements. I don't know. I mean, it's hard to say. Like it would. I think other factors would impact this method more than the number of lanes.
Okay.
Well, before we thank Michael, to wrap it up for today. I want to just mention that next Friday at the same time, same place, Smith Cerama School from the Oregon Bridge Delivery Partners will be presenting Diverging Diamond Interchanges, Answers to Frequently Asked Questions. So we hope we'll see you then. And let's give Michael a big hand.